There's a star closer to you right now than almost anything you have ever pointed a finger at in the sky, and you have never seen it. Not once. Not on the clearest night of your life. Not through the darkest desert air. Not even if you had the sharpest eyes of any human who ever lived. It is 4 light years away, which sounds far until you realize it is your nearest neighbor in the entire universe outside this solar system. And it is still, at this exact moment, sitting in a blind spot your eyes were never built to cover. That is not a metaphor. That is a hole in your biology. And once you understand why that hole exists, you will never look at a clear night sky the same way again. Here is the number that should stop you cold. Within about 17 light years of where you are sitting right now, there are somewhere close to 60 separate star systems. 60 suns, some paired up, some traveling alone, some dragging planets around with them, some burned out entirely. Of those 60, you can see 9. 9 with your own eyes, unaided, on a good night. That means for every star you have ever picked out and admired in your local sky, there are roughly 6 more sitting at the same distance or closer that you have never once laid eyes on. They are not behind anything. They are not blocked by clouds or light pollution or the curve of the Earth. They are simply too dim for the equipment installed in your skull. So if the brightest stars aren't the closest ones, why does it feel like they are? Why did every civilization that ever existed build its calendars, its mythologies, its entire understanding of the universe around Orion, around Sirius, around the North Star, when almost none of those objects are anywhere near us? That question is the whole reason this video exists. And by the end of it, you're going to understand something most people go their whole lives without knowing. The night sky is not a map of your neighborhood. It is closer to a highlight reel, and the highlights it shows you are, almost without exception, not your neighbors at all. Let's start with the instinct everybody has, because it's not a stupid instinct. It's actually correct almost everywhere else in your life. If you're standing in a dark parking lot and you see 2 lights, one brighter than the other, your brain assumes the brighter one is closer. Walk toward a candle, and it grows brighter. Walk away, and it fades. Headlights on a highway work the same way. Every single light source you interact with on the surface of this planet obeys that rule. Brightness equals proximity. And your brain has been trained on that rule since before you could talk. So when you look up and see Sirius blazing overhead, more brilliant than anything else in the sky, your gut tells you it must be close. And here's the cruel part. You'd be right. Sirius actually is one of our nearer neighbors, sitting at about 8.5 light years away. Your instinct gets confirmed. Case closed, right? Except Sirius is the exception that ruins everything else. It's the one star in the sky that happens to be both bright and genuinely nearby. And because it sits at the very top of both lists, the brightest stars and the nearest stars, it tricks you into believing those 2 lists overlap everywhere else. They don't. Sirius is doing double duty precisely because it's rare. It's a hot, young, white star, roughly twice as massive as our sun, and about 25 times more luminous. And it happens to also be close enough that its glow doesn't have far to travel before it reaches your retina. Almost nothing else in the visible sky can make that same claim. Take Rigel, the blue-white star anchoring the foot of Orion, one of the brightest points in the entire winter sky. Every instinct you have says it must be close. It is not close. Rigel sits somewhere around 860 light years away. The light hitting your eyes tonight left that star before the printing press existed. It is not a neighbor. It is a searchlight from a completely different chapter of human history. So extravagantly luminous, something like 120,000 times the output of our sun, that it can punch through 8.5 centuries of cosmic distance and still dominate your sky. Betelgeuse, marking Orion's shoulder, the reddish dying giant everyone has heard might explode someday, sits around 650 light years out. Deneb, one of the brightest stars in the summer sky, sits an almost absurd 2,600 light years away and pumps out something like 200,000 times the sun's energy just to remain visible from that distance. Polaris, the star that guided every sailor who ever trusted a compass rose, sits over 400 light years off, a yellow supergiant nearly 2,000 times more luminous than our sun. None of these are your neighbors. Every one of them is a monster of luminosity so extreme that ordinary distance simply fails to hide it. Now flip the question around. If the stars you can see are mostly not your neighbors, then who actually is? And the answer to that question is where this story turns genuinely strange, because your real neighbors are sitting out there right now, invisible, and some of them are stranger than anything a screenwriter could invent. Let's start at the very top of the list. The single closest star to our solar system, excluding the sun itself. Its name is Proxima Centauri, and it sits about 4.24 light years away. If your instinct about brightness and distance held up even a little, this should be one of the most obvious objects in the sky. It should have been the first star any civilization ever named. It wasn't named until 1915. Nobody knew it was there for the entire span of human civilization up to that point, because Proxima Centauri is not dim. It is invisible. Its apparent brightness sits at around magnitude 11, and the naked human eye, under the darkest, most perfect conditions achievable on this planet, tops out at around magnitude 6. That gap isn't small. Magnitude 11 is roughly 100 times fainter than what your eye can register. You could take a lifetime of perfect viewing conditions, and Proxima Centauri would still never once resolve into a visible point of light for you. The single nearest star in the entire universe outside our own sun is, and always has been, biologically off limits to human vision. It gets stranger. Proxima Centauri isn't just invisible, it's violent. It belongs to a category astronomers call flare stars, and unlike our calm, predictable sun, it periodically erupts in outbursts that would be genuinely dangerous to anything living nearby. In the spring of 2019, astronomers caught it in the middle of one of these flares and watched its ultraviolet brightness spike roughly 14,000 times in a matter of seconds. That's not a typo. 14,000 times in seconds. And it isn't a one-time event. This star throws off flares of that scale several times a year, like clockwork, a temper it apparently cannot control. Why does that matter to us? Because Proxima Centauri has at least one confirmed planet, discovered in 2016, roughly Earth-sized, sitting in the zone around its star where temperatures could, in theory, allow liquid water. Astronomers named it Proxima B, and for a moment when it was announced, plenty of people got genuinely excited about the idea of a habitable world just over 4 light years from home. Then the flare data came in. Researchers modeling the radiation environment around that planet concluded that a barrage like Proxima Centauri regularly produces could strip away the majority of a planet's ozone layer in a matter of years, not centuries, years. During one of the star's outbursts, the radiation reaching a planet's surface could be roughly 100 times the dose needed to kill even the toughest microorganisms known on Earth. One of the scientists who studied this put it about as bluntly as a scientist ever puts anything. A human being standing on that world during a flare would, in her words, have a bad time. And even setting the flares aside, Proxima B is stranger than anything close to home for another reason. It orbits its star so tightly, completing a full year in just 11 days, that gravity has almost certainly locked it in place, the way our moon is locked to Earth. One face of that planet points permanently toward its sun, trapped in an endless day that has lasted since the planet formed. The other face points permanently away, locked in a night that has never once seen a sunrise and never will. If anything could survive there at all, it would have to cling to the narrow ring of twilight running around the planet's equator, the only place where the eternal day and the eternal night meet. That is what our closest neighbor in the entire universe actually looks like once you get past the poetic idea of it. A violent, invisible ember orbited by a tidally frozen world split between permanent fire and permanent dark. Naturally, once people realized our literal nearest neighbor might have a rocky, potentially watery planet, someone tried to figure out how to get there. A well-funded initiative called Breakthrough Starshot proposed launching a fleet of tiny probes, each barely bigger than a postage stamp, and accelerating them with a massive ground-based laser array to a meaningful fraction of the speed of light, fast enough to reach Proxima Centauri within a human lifetime instead of tens of thousands of years. The project generated headlines around the world. It has not been cancelled outright, but the ambitious momentum it had years ago has quietly stalled, with the program's own director describing its status as being on hold, while pieces of the underlying research get folded into other efforts. And here's the number that explains why even a project with serious funding behind it struggles. Our fastest spacecraft ever launched, the Voyager probes, already decades into their journey out of the solar system, would need something on the order of 75,000 years to cover the same distance. 75,000 years to reach our closest neighbor. That is the gap between where our technology currently stands and where our curiosity wants to go. Right next door to Proxima Centauri, practically sharing its neighborhood, sit two more stars that are actually the two closest sun-like stars we have. Alpha Centauri A and Alpha Centauri B form a binary pair, orbiting each other the way a couple might slow dance across a room, and together they are bright enough that from the southern hemisphere they appear as the third brightest point of light in the entire sky. These two are the closest thing we have to a genuine twin of our own sun sitting nearby. Warm yellow stars, similar in size and temperature to the one keeping us alive right now. In 2024, using the largest space telescope ever built, astronomers thought they caught the faint signature of a giant planet moving through the light of one of these stars. When they looked again months later, hoping to confirm it, the signal had vanished back into the glare, and to this day it remains nothing more than an unconfirmed candidate, and maybe hovering at the edge of detection. So far, the pattern should already be unsettling you a little. Our nearest neighbor is invisible and dangerous. Our second nearest pairing is tantalizing but unconfirmed. It only gets more unusual from here, because the story of Barnard's star is, without exaggeration, one of the strangest cases of scientific whiplash in modern astronomy. Barnard's star sits just under 6 light years away, making it the second closest individual star system to our sun. It's ancient, likely somewhere around 10 billion years old, more than twice the age of our own sun, a coal that was already old when the Earth was still cooling into a solid ball of rock. And it moves. Of every star visible from Earth, Barnard's star has the highest proper motion of them all, drifting across our sky faster than any other point of light. Discovered through that very motion in 1916 by the American astronomer E. Barnard, who noticed a faint dot creeping across photographic plates faster than anything else in the frame. Here is where the story turns strange. In the 1960s, a respected astronomer studying this star's subtle wobble announced that he had found planets orbiting it. For years, textbooks and star charts treated this as settled fact. Then it fell apart. The wobble turned out to be nothing more than a mechanical flaw in his own telescope, a ghost created by the instrument, not the star. Decades later, in 2018, a new team announced a different discovery. A super-Earth, several times the mass of our own planet, tucked into the system. For roughly 3 years, this planet sat confirmed in the scientific literature. Then it also dissolved, exposed as an artifact of the star's own rotation rather than a genuine world. Twice, Astronomers were certain they had found something real circling this nearby star. Twice, the discovery turned out to be a reflection of their own hope rather than an actual planet. Then, finally, in October of 2024, using an instrument in Chile sensitive enough to detect a star trembling at something close to walking pace, a real planet was confirmed. Astronomers named it Barnard B, roughly half the mass of Venus, completing an orbit around its star in just 3 days, meaning it sits far too close and far too scorched for anything resembling life. By March of 2025, the count had grown to 4 confirmed worlds around this star, the smallest planets ever detected using that particular measurement technique. All 4 are crammed into orbits so tight they sit inside the zone where liquid water could theoretically survive. And a study published just recently concluded that every single one of them is almost certainly bone dry, described in the researchers' own language as extremely uninhabitable. A century of false starts, ghost signals, and withdrawn discoveries, and the payoff turned out to be 4 small, dry, scorched worlds. One of the scientists involved summed up the strange irony of it well. This is one of our closest cosmic neighbors, and we still barely understand it. There's one more twist to this particular star's story worth knowing. Barnard's star isn't just fast across our sky, it's genuinely racing toward us through space. In roughly 11,800 years, it will pass closer to our solar system than Proxima Centauri currently sits, briefly becoming the nearest star in the entire universe to our sun, before continuing on its path and receding back into the dark. Even the map we're building of our own neighborhood tonight is temporary. The street itself is slowly rearranging. Now, here's where things get almost uncomfortable, because the next star on our list of nearest neighbors, sitting just under 8 light years away, has never once been seen by a single human being in the entire history of our species. Not glimpsed, not squinted at, not mistaken for something else. Its name is Wolf 359, and it wasn't found through a telescope pointed by eye at all. It was pulled out of photographic plates in 1917 by the German astronomer Max Wolf. Plates that could gather light no living human retina could ever hold on to. And here's the detail that should genuinely unsettle you. Wolf 359 is not some rare oddity. It is, in a sense, the norm. Roughly 3 out of every 4 stars in the entire Milky Way are small, cool, red dwarfs almost exactly like it, and not a single one of them, anywhere in the galaxy, is bright enough for the naked human eye to detect. Sit with that for a second. The overwhelming majority of everything burning in our galaxy is a category of object that no human being has ever seen or ever will without a telescope. The galaxy you picture when you close your eyes, full of bright, distinct, twinkling points, is built almost entirely from the rare exceptions. The actual galaxy, the one that exists whether or not you can see it, is a vast, dim population of small red embers, and it has always surrounded us in total silence. Wolf 359 has no confirmed planets, and it's a flare star as well, prone to sudden violent eruptions of radiation without warning. A small, invisible furnace with a short temper. It picked up an odd bit of cultural fame decades after its discovery, when writers looking for a location to stage a fictional space battle chose this very star. This dim, unseen ember nobody on Earth has ever laid eyes on, specifically because of how obscure and unfamiliar it was. The real significance of Wolf 359 isn't the fiction attached to it. It's what it represents. Proof that the galaxy's most common inhabitant is one you will never personally witness. Which brings us back, finally, to the one star on this list everybody already knows. Sirius, sitting just over 8.5 light years away. The single brightest point of light in the entire night sky. Visible from nearly every inhabited place on Earth. named and steered by and mythologized by every seafaring culture in recorded history. Sirius earns its place on both lists, brightest and nearest, honestly. But it's hiding something. The man who first suspected it was the same astronomer who kicked off this entire era of measuring real distances to stars in the first place, Friedrich Bessel. In 1844, watching Sirius sway very slightly back and forth across the sky over years of careful observation, as though something invisible were gently tugging at it, Bessel predicted that a hidden companion had to be orbiting it. He wrote a line that, whether he knew it or not, became something like the founding principle behind everything we're covering tonight. The existence of countless visible stars proves nothing against the existence of countless invisible ones. Bessel died before his prediction was ever confirmed. 18 years later, in January of 1862, a telescope maker testing a brand new instrument in Massachusetts turned it toward Sirius and spotted a faint pinpoint of light, huddled close beside the blazing star, exactly where Bessel said something should be. It was the companion he had predicted, and it turned out to be the very first white dwarf ever seen by human eyes. A white dwarf is not a living star. It's a corpse. Sirius B, as it came to be known, was once the dominant star in that system, likely around 5 times the mass of our own sun, and it burned through its life ages ago before collapsing down into something almost impossible to picture. The entire mass of our sun crushed into a sphere roughly the size of Earth. Matter so compressed that a single sugar cube-sized chunk of it would weigh close to a ton on our planet, still radiating leftover heat at around 25,000 degrees and cooling, slowly, permanently, forever. It stopped functioning as an actual star well over 100 million years ago. So the single brightest, most familiar, most trusted star in our entire sky, the one every culture in history has looked up and found without effort, has spent the whole of recorded human history quietly orbited by a dead star's remains, close enough to be gravitationally bound, invisible to the naked eye, completing one full loop around its living companion roughly every 50 years. And Sirius B is not some rare oddity either. Within that same 17 light-year bubble around our solar system, there are at least 4 white dwarfs like it, 4 stellar corpses drifting through our immediate neighborhood, hidden in plain sight. Compare that number to the 9 stars total that your own eyes can actually pick out in that same volume of space, and the math gets genuinely strange. For roughly every 2 living, visible stars near us, there is a dead one nearby that we simply cannot see. Our neighborhood isn't just dimmer than it looks, it's quieter and colder, and holds more graves than anyone glancing upward would ever guess. Not every door on this street is quite so grim, though. Roughly 11 light years out sits Ross 128, a red dwarf that behaves almost nothing like its violent neighbors, where Proxima Centauri and Wolf 359 erupt without warning. Ross 128 is old and calm, a steady, quiet star that rarely flares at all. Circling it, confirmed back in 2017, is a planet called Ross 128b, at least 1 1/3 times the mass of Earth, completing an orbit every 10 days, sitting right at the inner edge of the zone where liquid water could theoretically exist. If there is a single door on this entire street where the light in the window isn't made of fire, this might be the closest thing to it. Hold that hope loosely, though, because being inside the habitable zone is not the same thing as actually being habitable. A planet that close to any red dwarf, even a calm one, is almost certainly locked in the same way Proxima B is. One face permanently baked in daylight, the other locked in permanent night. Any hope for mild conditions confined to a narrow ring of perpetual twilight, wrapping around the planet's middle. And there's a strange footnote to this particular star's story. In 2017, astronomers picked up an odd radio signal that appeared to be coming from the direction of Ross 128. And for about a week, a fair portion of the world quietly wondered whether we had just heard something. We had not. The signal turned out to be interference bouncing off our own communication satellites, our own machinery echoing back at us. The only voice we've ever picked up from that particular direction in space was, in the end, our own. Now let's talk about something the surveys themselves openly admit. We do not have a finished map of our own street. Not even close. Take Teegarden's star, sitting only about 12 light years away, nearer to us than several of the systems we've already covered. It's a small, old, dim red ember, calm and unremarkable, and it sat exactly where it is for the entire span of human civilization, through every era in which people were carefully cataloguing the night sky, and nobody noticed it was there until 2003. Not 2,000 years ago. Not 200 years ago. Within the lifetime of most people watching this right now. A star closer to us than plenty of the stars ancient civilizations named and worshipped went completely undetected until the 21st century, simply because no eye, and for most of history, no instrument either, was sensitive enough to notice it drifting there. Teegarden's star turned out to be worth the wait, at least on paper. In 2019, astronomers confirmed at least 2 Earth-mass planets orbiting it, both sitting inside its habitable zone. One recent careful study estimated the odds that the more promising of these 2 worlds has managed to hold on to any kind of atmosphere at all across the billions of years it's existed. And the number that came back was roughly 3 in 100. 3 chances in 100 that there's any air there at all, any sky capable of holding a cloud. It is, by some measures, one of the most Earth-like planets ever found anywhere in the sky. It is also almost certainly a bare, airless rock. Both of those things can be true at once, and that tension, hope colliding with hard probability, is going to come up again and again the deeper we go. A little further out, at roughly 12.5 light years, sits Captain's star. Discovered far earlier than Teegarden's, back in 1897, found through its unusually fast drift across the sky, the second fastest motion known at the time. What makes Captain's star strange isn't when it was found, it's where it came from. Unlike most of the stars in our immediate neighborhood, which orbit the galaxy roughly in step with our own sun, Captain's star belongs to the galaxy's halo population, tracing a steep, tilted orbit that carries it on a completely different path through the Milky Way. Its chemistry reveals that it formed in a far earlier chapter of galactic history, and current estimates put its age at somewhere around 11 billion years, more than double the age of our own solar system. This is a genuine relic, a wanderer that formed elsewhere in the galaxy's long history, and happens, for a little while in cosmic terms, to be passing directly through our neighborhood on its way to somewhere else entirely, invisible to every human eye that has ever looked in its direction. Roughly 12 light years away sits Lalande 21,185, first catalogued in the late 1700s by the French astronomer Jérôme Lalande, and it hovers right at the ragged edge of naked eye visibility, dim enough that only under the most extreme perfect viewing conditions could a sharp-eyed observer even begin to argue they'd glimpsed it. For every practical purpose across history, it simply wasn't there. And here's a fact that puts the scale of this hidden population into perspective. Within just 5 parsecs of our sun, roughly 16 light years, the most careful census work available, decades of patient ground-based observation from a research collaboration dedicated entirely to mapping our nearest stars, shows that red dwarfs make up close to 80% of every main sequence star in that volume. For every sun-like star sitting nearby, there are something like 15 to 20 red dwarfs keeping it company, unseen. For every hot, bright, blue-white star nearby, there might be over 100 red dwarfs sharing the same patch of space. The neighborhood isn't a balanced mix of equals. It's overwhelmingly dominated by the exact category of object your eyes are least equipped to register. And then, just when you think the list of hidden neighbors couldn't get any stranger, we arrive at a discovery that stunned the entire field of astronomy as recently as 2013. An event that proved even our most confident assumptions about our own street were incomplete. Sitting at roughly 6.5 light years away, closer to us than Barnard's star, closer than Wolf 359, closer than almost every neighbor we've discussed so far, is a pair of objects now known as Lumen 16, and until 2013, nobody on Earth knew they existed. Not the ancient astronomers, not the astronomers of the last century, not even the astronomers actively searching our immediate neighborhood with modern instruments, until an American researcher named Kevin Luhman noticed something strange while sifting through infrared survey data. A single point of light appeared to have shifted position slightly between two separate observation passes taken years apart. The same kind of telltale drift that revealed Barnard's star a century earlier, except this time the drift showed up not in visible light, but in infrared, wavelengths completely outside what a human eye or an ordinary telescope could ever pick up. When Luhman traced that faint shifting point back through older archived data, he found it had actually been captured multiple times over more than a decade by earlier infrared surveys, sitting there the entire time, flagged by nobody, because nothing about it stood out as unusual until its motion was measured. Follow-up observations with a large telescope in Chile resolved the single point into two separate objects, orbiting each other closely, the third closest star system to our own sun in the entire universe, hiding in plain sight roughly 6.5 light years away, undiscovered until barely more than a decade ago. Here's the part that makes it even stranger. Lumen 16 isn't even made of true stars. Both objects are brown dwarfs, a category of object that occupies a strange middle ground between a planet and a star, massive enough to have formed the same way a star does, collapsing out of a cloud of gas and dust under its own gravity, but never quite massive enough to ignite the sustained nuclear fusion that would make it a genuine, self-sustaining star. Picture a kettle that was heated once during its formation and then permanently unplugged. It glows faintly from the leftover heat of its own birth, and then it spends the rest of its existence slowly, endlessly cooling down. That's a brown dwarf, two of them orbiting each other, sitting closer to our solar system than almost every star that has ever appeared in a constellation. And we only found out they were there within the last decade and a half. Since their discovery, astronomers have done something with Lumen 16 that had never been done for any brown dwarf before. They mapped its weather. By watching subtle changes in its brightness over the course of just a few hours, researchers identified patchy regions of clouds shifting and evolving across its surface, the first weather map ever produced for an object of this kind. Proof that these failed stars aren't static, inert lumps. They're dynamic worlds with genuine churning atmospheres, not unlike the storm bands you'd find on Jupiter, just close enough to be counted among our nearest neighbors and unseen by human eyes for the entire span of civilization before 2013. If Lumen 16 sounds strange, the very next discovery down the list is stranger still, and it holds the record for the coldest object ever found this close to our solar system. Just 1 year after Luhman's discovery, in 2014, the very same researcher announced another find, a single object this time, catalogued as WISE 0855, sitting at roughly 7.5 light years away, making it the fourth closest known system to our sun, just behind Lumen 16 and just ahead of Wolf 359. Its motion across the sky was enormous, among the fastest ever measured for anything beyond our solar system, the unmistakable signature of an object sitting extremely close to us. But its motion isn't the detail that makes this object remarkable, its temperature is. Current estimates put the surface temperature of WISE 0855 at somewhere around minus 25 degrees Celsius, roughly minus 13 Fahrenheit. That is colder than the freezing point of water. That is colder than a winter night in most temperate cities on this planet. That is, in the most literal sense, comparable to the inside of a kitchen freezer. And it is sitting less than 8 light years from the chair you're in right now. At that temperature, this object emits essentially no visible light whatsoever. It radiates almost entirely in wavelengths, so far into the infrared that even the Hubble Space Telescope, one of the most powerful optical instruments ever put into orbit, could barely detect it at all. And only after hours of accumulated exposure time produced what amounted to the faintest possible smudge on an otherwise blank patch of sky. To any instrument relying on visible light, there is nothing there. Empty space. And yet this object sits closer to our solar system than every star in the sky, except 3 other systems in the entire galaxy. Its estimated mass falls somewhere between roughly 3 and 10 times the mass of Jupiter, placing it right at the blurry boundary between what we'd call a brown dwarf and what we'd call a rogue planet. An object massive enough to have possibly fused a small amount of deuterium briefly during its youth, but nowhere close to ever becoming a genuine star. Whether the correct label for it is failed star or wandering world depends more on definitions than physics. And honestly, out 7.5 light years, freezing quietly in the dark, it probably doesn't care which one we choose. Its discovery was only possible because a specific mission had been built from the ground up to look for exactly this kind of object. That mission is worth understanding because it's the single biggest reason we know as much as we do about our hidden neighborhood today. In December of 2009, NASA launched a space telescope called WISE, the Wide Field Infrared Survey Explorer, designed specifically to scan the entire sky at infrared wavelengths invisible to the human eye and to ordinary optical telescopes. Its optics were cooled to somewhere below negative 400 degrees Fahrenheit using a tank of frozen hydrogen, because even the faint residual warmth Earth's own atmosphere is full of water vapor and carbon dioxide that absorbs and re-emits infrared radiation, creating a bright, noisy background glow in exactly the wavelengths astronomers needed to see through clearly. Trying to spot a faint, cold brown dwarf from the ground is a little like trying to photograph a single candle flame while standing inside a bonfire. The background simply overwhelms the signal. Moving the telescope into space, above the entire atmosphere, eliminated that problem in one stroke, and the payoff was a level of sensitivity to cold, dim objects that no observatory on the ground could match, no matter how large its mirror or how remote its mountaintop. There's a piece of this story, though, that has nothing to do with billion-dollar spacecraft or professional astronomers with doctoral degrees, and it might be the most human part of the entire tale. WISE gathered so much data, more than 2 billion individual objects spread across upward of 30 trillion pixels of sky coverage, that no research team on Earth, no matter how large, could possibly examine all of it carefully enough to catch every faint, slowly moving object hiding inside it. So in 2017, NASA opened the search to everybody. A citizen science project called Backyard Worlds, Planet 9 invited ordinary people, anyone with an internet connection and a bit of patience, to look through short animated loops of WISE images and flag anything that appeared to shift position between frames, exactly the kind of motion that reveals a nearby, previously unknown object. More than 200,000 volunteers eventually took part, scanning through the same billions of pixels of infrared data from their own homes in dozens of countries on their own time. Retired engineers, school teachers, college students with no formal astronomy training at all. People who simply liked the idea of looking for something nobody else had found yet. And they found things. Real things. More than 40 of these volunteers ended up as named co-authors on peer-reviewed scientific papers, their names printed directly alongside professional astronomers, credited for genuine discoveries. Just this year, in a landmark result published in the spring of 2026, the Backyard Worlds collaboration announced something extraordinary. Over 3,000 new, motion-confirmed brown dwarf candidates, found largely through this volunteer effort, effectively doubling the entire known population of these objects in one publication. Somewhere out there right now, a retired machinist scrolling through infrared images on a laptop after dinner has a genuine chance of spotting an object closer to our solar system than the star that sits at the center of half the constellations you learned as a kid. At this point, you might be wondering something reasonable. If these stars are genuinely this close, why can't we just build a bigger telescope and see them the normal way, in ordinary visible light, the same way we see everything else? The answer isn't about telescope size at all. It's about physics, and once you understand it, you'll realize your eyes were never failing to do their job. They were doing exactly what evolution built them to do, and that job never included seeing most of the universe around you. Every object with a temperature above absolute zero radiates energy, and the hotter that object is, the shorter the wavelength at which it radiates most strongly. This relationship, worked out in the late 1800s and known as Wien's displacement law, explains everything from the color of a blacksmith's glowing iron to the color of a star. Our sun, with a surface temperature of around 5,700 degrees Celsius, radiates most strongly in the yellow-green part of the visible spectrum, right around 500 nanometers. And here's the detail that matters more than anything else in this entire video. Human eyes are most sensitive to light at almost exactly that same wavelength, somewhere around 555 nanometers. That is not a coincidence. Hundreds of millions of years of evolution under this one specific star tuned our vision generation after generation to catch the exact kind of light our sun happens to produce most abundantly. Your eyes are not a general purpose cosmic detector. They are custom built hardware, calibrated to one particular star, and nothing else. Now apply that same physics to a red dwarf. Surface temperatures on these stars typically sit somewhere between about 1900 and 3500 degrees Celsius, dramatically cooler than our sun, and Wien's law tells us exactly what that means. Their peak radiation shifts well into the near infrared, wavelengths between roughly 800 and 1200 nanometers. The human eye's sensitivity effectively ends around 700 nanometers. Past that point, as far as your biology is concerned, there's nothing there. A red dwarf isn't dim because it's failing to produce light. It's producing plenty of energy. It's simply producing that energy in a color your eyes were never built to register, radiating in a language your retina doesn't speak. Push the temperature down further into true brown dwarf territory, and the peak radiation shifts even further into the mid-infrared, wavelengths of several thousand nanometers, so far removed from anything visible that even many specialized astronomical instruments struggle to pick it up without purpose-built cooled detectors. This is the actual mechanism behind everything we've covered so far. These objects aren't hidden behind dust, or blocked by distance, or concealed by some conspiracy of nature. They are radiating continuously, right now, a handful of light years from where you're sitting, fulfilling their role as functioning stellar objects exactly the way they're supposed to. They are simply doing it in a part of the spectrum that falls completely outside the narrow slice of light your particular species happens to be able to perceive. If your eyes had happened to evolve under a cooler, redder star instead of our own, this entire conversation would run in reverse. Red dwarfs would blaze across your sky like familiar lanterns, obvious and bright, while stars like Sirius and Rigel would appear pale and unremarkable by comparison. The bias was never out there in the universe. It has always been sitting inside your own skull. Here's a number that should reframe how you think about the word ordinary the next time you hear someone describe our sun that way. Our sun is often called an average, typical, unremarkable star. And in a narrow sense, that's true. It's not exceptional among the handful of bright stars visible in the sky. But among all stars that actually exist across the galaxy, our sun sits comfortably in the upper tier, brighter than somewhere around 85 to 90% of all main sequence stars in the Milky Way, more massive than roughly 90% of them. When natural selection calibrated your eyes to detect the kind of light our sun produces most generously, it wasn't calibrating you to notice typical stars. It was calibrating you to notice the uncommon, energetic minority, while leaving you essentially blind to the common, dim majority that makes up most of the galaxy around us. This uneven distribution isn't some strange coincidence either. It's baked directly into how stars form in the first place. When a massive cloud of gas and dust collapses under its own gravity and fragments into new stars, the resulting objects span an enormous range of masses. But low mass fragments vastly, overwhelmingly outnumber high mass ones. This pattern, first carefully characterized by the astronomer Edwin Salpeter back in 1955, and refined many times since by researchers studying star-forming regions across the galaxy, holds up again and again wherever it's tested. For roughly every star born with 10 times the mass of our Sun, something on the order of 1,000 stars are born with only a tenth of the Sun's mass. That ratio isn't subtle. It's the difference between a rare, spectacular exception and an assembly line running at full production. The galaxy manufactures small, dim, red stars in staggering abundance, and it produces bright, massive ones only rarely, as almost accidental outliers. And here's a detail about red dwarfs that might be the strangest fact in this entire story. Stranger even than the invisible neighbors themselves. Not a single red dwarf that has ever formed anywhere in the history of the universe has yet died of old age. Our sun has a total projected lifespan of roughly 10 billion years, and it's already about 4.5 billion years into that clock. A red dwarf with around half the sun's mass will remain actively burning for something on the order of 80 billion years. A red dwarf with only 20% of the sun's mass could burn for several 100 billion years. And the smallest ones, sitting right at the minimum mass needed to sustain fusion at all, are projected to keep burning for trillions of years. Not billions, trillions. The universe itself is only about 13.8 billion years old. Even the very first red dwarfs that ever ignited, in the earliest chapters of cosmic history, are still sitting comfortably in the early stages of lifespans that will vastly outlast everything else in the sky. Every white dwarf we found, every collapsed stellar corpse like the one orbiting Sirius, represents a star that has already died. The universe's graveyard so far contains 0 dead red dwarfs. Every single one that has ever formed is, right now, still quietly burning in the dark. The reason for that staggering longevity comes down to an elegant piece of internal plumbing most people never think about. Stars like our sun burn hydrogen only in a small, dense core, leaving vast reserves of untouched fuel sitting uselessly in their outer layers for the entire span of their lives. Fuel that never gets consumed, even as the star eventually dies. Red dwarfs below a certain mass threshold work completely differently. Their interiors are fully convective, meaning hot material continuously rises from the core toward the surface, while cooler material sinks back down, mixing the entire star from center to edge in a slow, continuous churn. Every single atom of hydrogen fuel eventually gets cycled down into the fusion core and used. Nothing gets stranded in an inaccessible outer shell. It's a staggeringly efficient design, a stellar engine built to waste almost nothing, and the trade-off for that efficiency is a lifespan that makes our own sun's 10 billion year run look almost hasty by comparison. Given how common these stars are and given how long they live, it should come as no surprise that the search for planets beyond our solar system has increasingly turned toward exactly this category of star, and the payoff has been enormous. Because red dwarfs are so much smaller than sun-like stars, a planet passing in front of one blocks a proportionally larger fraction of its light, making that dip in brightness far easier to detect from Earth. A planet's gravitational tug on a small, lightweight red dwarf also produces a proportionally larger wobble, easier to measure with modern instruments than the same tug would produce on a heavier, sun-like star. These advantages have turned red dwarfs into the most productive hunting ground in the entire search for small, rocky, Earth-sized worlds. Roughly 40 light years away sits a system that became the most famous example of this pattern almost overnight. A modest red dwarf named TRAPPIST-1. Around it orbit 7 planets, all close to Earth's size, and remarkably, 3 of them sit inside the star's habitable zone at the same time, a genuinely rare arrangement that turned this single, unremarkable, invisible to the naked eye star into one of the most intensely studied planetary systems ever found. It's not an isolated case either. Red dwarf planetary systems, once thought to be a curiosity, have turned out to be closer to the norm than the exception. And if even a modest fraction of the roughly 200 billion or so red dwarfs scattered across our galaxy host rocky planets in their habitable zones, the total number of potentially habitable worlds in the Milky Way runs into the tens of billions. The overwhelming majority of that habitable real estate would orbit stars no human eye has ever seen, and likely never will without a telescope. Habitability around a red dwarf remains a genuinely open, actively debated question in astronomy, and it's worth being honest about why. Because the same qualities that make these stars so long-lived and so easy to search for planets around also make them dangerous places to actually live. Young red dwarfs in particular can be hundreds of times more magnetically active than our mature, relatively calm sun, capable of producing superflares that would dwarf anything ever recorded from our own star. And because a planet has to orbit extremely close to a red dwarf just to receive enough warmth to support liquid water, most of those potentially habitable worlds are almost certainly tidally locked, one hemisphere baking in permanent daylight, the other frozen in permanent night, with any hope for moderate conditions confined to a narrow twilight band circling the planet between the two extremes. Whether complex life could ever take hold and persist under conditions that alien remains one of the genuinely unresolved questions in modern astrobiology, and anyone who tells you the answer is obviously yes or obviously no is guessing well past what the evidence currently supports. Not every attempt to find a habitable world nearby has held up under scrutiny, though. And one particular story from this same search deserves to be told honestly, because it's as much a story about human hope as it is about astronomy. About 20 light years out sits an unremarkable red dwarf catalogued as Gliese 581. For a few short years, it became arguably the most famous star system in the world that wasn't our own. In 2010, astronomers announced the discovery of a planet called Gliese 581g, roughly Earth-sized, sitting squarely in the comfortable middle of its star's habitable zone, not scorched near the inner edge, not frozen near the outer edge, right in the center of the temperate band. It was hailed publicly as the first genuinely habitable planet ever found beyond our own solar system. One of its discoverers cared enough about the find to give it an informal, human nickname. Artists produced illustrations imagining its oceans and its rocky coastlines glowing beneath a dim red sky. For a little while, a real portion of the public believed we had actually found a second Earth, close enough to seriously dream about. Then, carefully, patiently, other researchers went back through the data. What they found was that the signal that had been interpreted as a planet was almost certainly nothing more than the star's own internal activity, its own subtle pulsing and churning, misread as the gravitational tug of an orbiting world. One of the astronomers who worked through the original numbers stated the conclusion about as plainly as it can be stated. The planet does not exist. The most beloved, most talked about nearby world ever announced turned out to be a ghost, a shape drawn by hopeful researchers across an otherwise empty patch of data. Real planets have since been confirmed around Gliese 581, worlds astronomers are now confident are genuinely there, But the one the public fell in love with first was never real at all. And here's a detail that makes that story linger a little longer than it probably should. Back in October of 2008, using a large radio dish, a project gathered several hundred short messages written by hundreds of thousands of ordinary people from around the world and beamed them directly at Gliese 581. That signal is still traveling through space right now, and current estimates put its arrival sometime in the next few years. It will reach a dim red star where the one world we most wanted to find was never actually there. And as far as anyone currently knows, nothing will ever answer it. Not every recent development in this story ends in disappointment, though, and the newest tools available to astronomers are starting to do something that would have sounded like science fiction only a few years ago. Actually photographing these worlds directly, rather than inferring their existence from a wobble or a shadow. In July of 2024, using the largest space telescope ever launched, astronomers captured an actual image, not a graph, not an inferred silhouette, an actual photograph of a giant planet orbiting a nearby star called Epsilon Indi, sitting around 12 light years away. It's one of the coldest planets ever directly imaged anywhere, hovering close to the freezing point of water rather than blazing hot like most directly photographed exoplanets tend to be. Later analysis of that same faint point of light revealed something remarkable. Clouds of water ice hanging in its distant, frigid sky. We are no longer limited to inferring these worlds exist from indirect mathematical signatures. We have started, faintly, imperfectly, to actually look through their windows. One more nearby signal is worth mentioning before we step back and take in the full shape of everything we've covered, because it hints at something we haven't fully solved yet either. A small red dwarf called YZ Ceti, sitting roughly 12 light years away, produces a strange repeating pulse of radio light. No serious astronomer believes this is any kind of intentional signal, and nothing about it suggests anything other than natural physics at work. What it may represent instead is something quieter, and, in its own way, more meaningful. Possible evidence of a small rocky planet nearby, carrying its own magnetic field. The star and the planet tugging at each other's magnetism, and producing a faint, rhythmic radio signature as they interact. That same kind of magnetic shield is the exact mechanism that has allowed our own planet to hold onto its atmosphere and its oceans for billions of years, instead of having them stripped away by the sun's radiation. If that interpretation holds up under further study, it would mark one of the first pieces of direct evidence we've ever found for a magnetic field on a small planet outside our solar system, discovered around a star that, like nearly everything else in this story, no human eye has ever seen. Before we go any further, it's worth pausing on how we ever learned to measure any of this in the first place. Because for most of human history, nobody had the faintest idea how far away any star actually was. A star was just a point of light. No depth, no context, no way to sort the near from the far. That changed in the winter of 1837, sliding into 1838, in the Prussian city of Königsberg, where an almost inhumanly patient astronomer named Friedrich Bessel spent well over a year tracking a single, faint, completely unremarkable star in the constellation Cygnus. A dim pairing catalogued as 61 Cygni, measuring the tiny, almost imperceptible way its position seemed to shift as the Earth swung from one side of its orbit around the Sun to the other. Most nights, the star barely appeared to move at all, but measurement by careful measurement, a number slowly emerged out of the noise, and Bessel determined that this faint, forgettable star sat roughly 10 light years away. For the first time in the entire span of human existence, someone knew in real, calculable distance how far it actually was to a neighboring star. When the news reached England, the astronomer John Herschel captured the moment perfectly, saying that the sounding line into the ocean of stars had at last touched bottom. For thousands of years, humanity had stared out into the dark, with no way to measure its depth. Now, finally, the line had gone down and struck something solid. There's a quieter, sadder footnote buried right alongside that triumph, and it deserves to be told, because it's a genuinely human story about hesitation. Far to the south, at the Cape of Good Hope, a Scottish astronomer named Thomas Henderson had actually measured the distance to a different star, Alpha Centauri itself, our nearest sun-like neighbor, roughly 5 years before Bessel published his own result. Henderson had the numbers in hand. He simply didn't trust them enough to publish. Checking and rechecking, doubting himself, hesitating through season after season while his data sat unpublished. By the time he finally worked up the confidence to share what he'd found, Bessel's measurement of 61 Cygni was already in print, and the credit for humanity's first real stellar distance measurement went to someone else. The very first working map of our neighborhood was almost Henderson's discovery, and he lost that place in history to nothing more than his own caution and one wasted season of second guessing. That measurement technique, called parallax, watching how a nearby star's position appears to shift slightly against the distant background as Earth moves around the Sun, remained the gold standard for measuring stellar distances for well over a century, gradually refined and applied to more and more stars as instruments improved. In 1989, the European Space Agency launched a dedicated satellite called Hipparcos, specifically to measure parallax distances with far greater precision than any ground-based observation could achieve. And by the time its mission ended, it had produced reliable distance measurements for over 100,000 stars, cementing the picture that red dwarfs genuinely do dominate the local stellar population, even as its optical design meant it still couldn't reach the very faintest, coolest members of that population, or any brown dwarfs at all. The mission that finally picked up where Hipparcos left off, and pushed the whole project to a scale nobody had previously imagined, was Gaia, launched by the European Space Agency in 2013, and operating until it was retired in January of 2025. Over more than a decade, Gaia measured the positions, distances, and motions of nearly 2 billion stars with a level of precision that reshaped huge portions of modern astronomy, confirming known red dwarfs, refining their distances, and identifying new ones that earlier surveys had missed entirely. But even a mission this ambitious had a blind spot, because it operated primarily at optical wavelengths, the same narrow band of light your own eyes are limited to. The very coolest, faintest red dwarfs, sitting right at the bottom of what a star can be, pushed right up against the edge of what Gaia could detect at all, and brown dwarfs, radiating almost entirely in infrared, were largely invisible to it altogether. The single most complete stellar census ever assembled, cataloging nearly 2 billion individual objects, still has a brown dwarf-shaped gap running straight through it, a gap that only dedicated infrared missions like WISE and the volunteers who combed through its data by hand have ever been able to fill. Here's a question worth sitting with for a moment before we move toward the end of this, because I think it says something true about how we actually operate as a species. If the volume of space closest to our own sun, the single easiest region of the entire universe to study, the place where distances are shortest and every signal is strongest, still contains objects we're finding for the first time within the last few years, what does that tell you about everything sitting farther out that we haven't even begun to properly examine? Drop your honest answer in the comments, because I'm genuinely curious whether that thought excites you or unsettles you, and I don't think there's a wrong answer either way. Let's take a step back now and lay the whole picture out at once. Because on its own, each individual star we've covered tonight is just one strange story. Stacked together, they tell you something much larger about the true shape of the space immediately surrounding us. Within roughly 10 light years of where you're sitting right now, astronomers have confirmed at least 9 separate systems, containing something like 14 or more individual stellar and substellar objects. Of those 14, exactly 3 can be seen with the unaided human eye from anywhere on Earth: Sirius and the 2 bright members of the Alpha Centauri pair. Every other object in that entire volume, Proxima Centauri, Barnard star, both members of Lumen 16, WISE 0855, Wolf 359, Leyland 21185, every single one sits completely beyond what human vision was ever built to detect. 3 visible objects, 11 or more invisible ones, sharing the exact same small pocket of space immediately around our sun. Push that boundary out further to 25 light years, and the pattern doesn't soften, it intensifies. Within that larger volume, astronomers have catalogued hundreds of individual stellar systems, the overwhelming majority of them dim red dwarfs sitting far below the threshold of naked eye visibility. A steadily growing number of confirmed brown dwarfs, detectable only through infrared surveys, and a scattering of white dwarfs. The collapsed remnants of stars that finished burning long ago, similarly faint and easy to overlook. Out of all of it, only a modest handful, perhaps a few dozen systems at most, are bright enough to register as a visible point in an ordinary night sky. Everything else populates that same neighborhood in complete silence, contributing gravity, contributing mass in a growing number of cases, contributing entire planetary systems of their own, and contributing absolutely nothing to what any human being has ever visually experienced looking upward. This mismatch between what your eyes report and what actually surrounds you isn't just an astronomical curiosity, it reaches directly into how every human culture that has ever existed understood its place in the universe. For thousands of years, civilizations built their calendars, their navigation systems, their entire mythological frameworks out of whatever happened to be visible overhead. Constellations like Orion, the Big Dipper, Cassiopeia, Scorpius feel like genuine architecture, like the stars forming that must be somehow related, gathered together into real neighborhoods, sharing real space. They are not. The stars inside any given constellation typically share no physical relationship with each other whatsoever. They're scattered across wildly different distances, sometimes separated from one another by hundreds of light years of empty space, and they only appear grouped together because they happen to lie in roughly the same direction as seen specifically from Earth. The 3 stars forming Orion's belt, which look to your eye like a tight, deliberate, orderly line, actually sit at distances ranging from around 1200 to 2000 light years away from each other, separated by gulfs of space that dwarf anything in this entire video so far. Move your vantage point by even a modest distance, a few dozen light years in any direction, and every familiar constellation you've ever learned would completely dissolve, replaced by patterns nobody on Earth has ever seen and nobody would recognize. What every constellation actually represents then is a brightness map, not a proximity map, a projection of the galaxy's most luminous outliers onto the inside of an imaginary sphere centered on wherever you happen to be standing. It tells you which direction the most powerful stellar furnaces happen to lie relative to your position. It tells you essentially nothing about what's actually close to you. The framework humanity spent 10,000 years of recorded history constructing. Every myth, every seasonal calendar, every navigation system ever trusted by a sailor crossing open ocean at night was built almost entirely out of the wrong stars. Not because anyone was wrong to trust their eyes, but because nobody had any way of knowing their eyes were only ever showing them a rare, unrepresentative sliver of what was actually there. And here's the part of this story that I think deserves to be said plainly, because it's easy to make this sound like some kind of conspiracy or cosmic trick, and it genuinely isn't one. This was never a failure of science, and it was never a case of these objects being permanently unknowable. Every star we've discussed tonight has now been found, measured, and catalogued. Infrared missions have mapped thousands of brown dwarfs. Parallax surveys have pinned down the distances to our nearest red dwarfs with extraordinary precision. Citizen scientists working from their own homes have doubled the known population of an entire category of object in a single published study. None of this information is missing from human knowledge anymore. It's sitting in accessible databases right now, available to anyone curious enough to go looking. The part that should actually stay with you isn't what science failed to find. It's what your own biology failed to show you. For the entire prior span of human existence, for roughly 300,000 years of anatomically modern humans looking up at the night sky, every single one of us believed, without any reason to doubt it, that we were looking at an honest picture of our cosmic surroundings. We were not. We were looking at a narrow, spectacularly unrepresentative sample of it, filtered through a biological instrument that happened to be calibrated for one specific, somewhat atypical star, and functionally blind to the overwhelming majority of everything actually surrounding us. The sky you grew up trusting wasn't lying to you out of malice. It simply never had the physical capacity to show you the whole truth in the first place. So try this with me for a second, because I think it's the clearest way to actually feel the difference between the sky you think you know and the sky that's actually there. Picture your eyes suddenly rewired, just for tonight, tuned not to the yellow-green light our sun floods us with, but to the near-infrared instead, the range where red dwarfs and brown dwarfs pour out most of their energy. Step outside and look up with those new eyes, and the sky you grew up with would essentially collapse. Orion's familiar outline would fade to almost nothing, its brilliant blue-white giants reduced to faint, forgettable specks. Rigel would nearly vanish. Deneb would disappear completely. The entire bright architecture that every human culture has spent 10,000 years mapping mythology onto would drop away within seconds. And in the space where all of that used to be, something else would rise to take its place. The gaps between stars, the parts of the sky that have always looked genuinely empty, would begin filling in with dim, steady points of light, emerging out of what had been total darkness a moment earlier. Proxima Centauri would glow, faint but unmistakable, 4 light years away, exactly where it's always been. Barnard's star would resolve clearly, no longer buried in the noise. Lumen 16 would appear as 2 close warm points sitting side by side. WISE 0855 would register as a faint thermal smudge, cold, but no longer invisible. None of these objects would have moved an inch. They'd simply become visible because the only thing standing between you and them all along was never distance. It was the specific, narrow slice of the electromagnetic spectrum your particular species happened to evolve the ability to see. The sky wouldn't get emptier under those new eyes. It would get dramatically fuller, and the night you always assumed was complete would reveal itself as a thin, misleading sketch drawn over a much richer picture that had been sitting there the entire time, waiting for an instrument capable of finally showing it to you. None of this makes the actual sky you see with your actual eyes any less worth looking at, by the way. And I want to be clear about that before we close this out, because it would be easy to walk away from a video like this feeling like the whole thing was some kind of letdown. It isn't. Sirius will keep blazing exactly the way it always has. Orion will keep rising every winter, unchanged, ancient, and genuinely beautiful. The constellations your grandparents pointed out to you, and maybe the ones you've pointed out to someone else since, will keep meaning whatever they've always meant to you, and nothing in tonight's video takes that away. What changes, if anything, is what you now understand is sitting just underneath that beauty, quietly, in wavelengths you'll never personally see. A whole second neighborhood, dimmer, colder, far more crowded than the one on display, existing right alongside the one you already love, not instead of it. What we've walked through tonight, door by door, all comes back to a single idea that's worth carrying with you long after this video ends. The universe closest to you, the objects nearest to the only planet you have ever known, were never hidden by any conspiracy, and they were never actually missing. They were radiating right where they've always been, continuously, patiently, for billions of years in most cases. And the only thing that ever stood between you and seeing them was the particular narrow, star-specific hardware installed behind your own eyes. You have spent your entire life surrounded by neighbors you have never once seen, and, without a telescope, never will. They are still out there right now, exactly as you finish hearing this sentence, cooling, flaring, orbiting, some of them possibly hosting worlds of their own, waiting for nothing in particular, certainly not for you to notice them, just continuing to exist in the dark the way they always have. And the honest, almost uncomfortable truth underneath everything covered tonight is this: the list is not finished. There are almost certainly more objects sitting within 10 or 15 light years of where you are right now that no survey, no citizen scientist, no infrared telescope has caught yet, simply because they're too cold, too faint, or moving in a direction that hasn't tipped off the instruments, watching for exactly that kind of motion. Every few years, the list of our nearest known neighbors quietly changes again. A new object gets confirmed, an old distance gets refined, and the map shifts a little further away from the one we grew up trusting. If that thought stayed with you at all tonight, if some small part of you is now looking forward to the next discovery, the same way you'd look forward to meeting an actual new neighbor, that's worth telling me about too. Write down which one of tonight's objects you'd want to visit first if distance was somehow no object at all. And stick around, because the next stop on this street is even stranger than anything we covered tonight. Let's go back to that street and knock on a few more doors, because there's a whole cluster of nearby systems we haven't touched yet, and each one adds another piece to the picture of just how crowded and how invisible our actual neighborhood really is. Start with 61 Cygni, the very star Bessel used to make that first historic distance measurement back in 1838. It sits at roughly 11.5 light years away, and it earned an old nickname long before its distance was known. Astronomers of the time called it the Flying Star, because of how noticeably fast it drifted across the sky compared to everything around it. The exact same kind of telltale motion that would later reveal Barnard's star, Wolf 359, and dozens of other hidden neighbors. It's actually a binary system. 2 orange dwarf stars orbiting each other, cooler and dimmer than our sun, but not quite as extreme as the red dwarfs we've spent most of tonight on. At magnitude 5, it sits close enough to the edge of naked eye visibility that under genuinely dark skies, away from any city light, a patient observer with good eyesight can actually pick it out. Faint and easy to miss. A star that helped unlock the entire scale of the universe, sitting almost unnoticed in plain sight the whole time. A little further out, at around 11.6 light years, sits Groombridge 34, another red dwarf pair, first catalogued in the early 1800s and confirmed decades later to be a genuine nearby binary system. Neither star is visible without help. And at 10.5 light years, there's Epsilon Eridani, one of the closer sun-like stars in our neighborhood. Technically bright enough to just cross the threshold of naked eye visibility at around magnitude 3.7. Here's the thing about Epsilon Eridani, though. Even though it's technically visible, almost nobody has ever consciously picked it out. It sits surrounded by brighter, flashier neighbors in the sky. A modest, unremarkable point of light, easily lost in a crowd of far more distant but far more luminous stars. It's a young system too, by stellar standards, somewhere under 1 billion years old, with at least one confirmed giant planet and evidence of multiple debris belts still settling into more stable orbits. Essentially a preview of what our own solar system might have looked like billions of years ago, sitting a little over 10 light years away and almost entirely overlooked. Push out to just under 10 light years and you hit Ross 154, a red dwarf flare star even more volatile than some of the others we've covered, capable of brightening dramatically within minutes before fading back down, a genuinely unpredictable neighbor. A little further, at just over 10 light years, sits Ross 248, another red dwarf, notable mostly for an odd bit of astronomical trivia. In roughly 36,000 years, its own motion through the galaxy will carry it closer to our Sun than Proxima Centauri currently sits, briefly making it, for a relatively short cosmic window, the nearest star to Earth, before it too continues on its way and drifts back into obscurity. Our current map of the nearest stars isn't just incomplete, it's actively temporary, rearranging itself constantly on timescales that dwarf human history, but are still, in the grand scheme of the galaxy, remarkably fast. At just over 11 light years sits Lacaille 9352, first noted in the 18th century by the French astronomer Nicolas Louis de Lacaille during an ambitious survey conducted from the Cape of Good Hope, though its true proximity to us wasn't confirmed until parallax measurements grew precise enough generations later to actually calculate its distance properly. At magnitude 7.3, it hovers frustratingly close to naked eye visibility without ever quite crossing the line, close enough to feel like it should be visible, too faint to ever actually be seen. And then there's a system that deserves special attention because it broke a record that had stood for decades. At roughly 11.9 light years sits GJ1061, confirmed as a genuine nearby neighbor through the same kind of careful, patient survey work that revealed most of the stars on this list. 3 planets have been detected orbiting it, and at least one appears to sit inside the star's habitable zone. Another entry in the growing pile of potentially temperate worlds circling stars that spent the entire span of human civilization completely unknown to us. Discovered not because they were bright, but because dedicated researchers kept pointing sensitive instruments at exactly the kind of dim, easily overlooked object most of the sky's history had simply ignored. Here's a pattern worth naming directly, because by now it should be obvious. Every single one of these systems was found the same way. Not by someone noticing a bright point of light and getting curious, but by careful, repeated, patient measurement, comparing images taken years apart, watching for the faint telltale drift that separates something genuinely close from something merely distant and bright. Proximity, it turns out, has almost nothing to do with how a star gets discovered. It has everything to do with how carefully anyone bothers to look. Now, let's go deeper on the brown dwarfs, because we only scratched the surface earlier, and this category of object genuinely deserves its own extended stop on this tour, since it represents the most recently discovered, most alien, and in some ways most misunderstood class of nearby neighbor we have. A brown dwarf forms the exact same way a star does. A cloud of interstellar gas and dust begins collapsing under its own gravity, the material at its center compressing and heating as it falls inward. In a successful star, that compression eventually drives the core temperature above roughly 4 million degrees, hot enough to ignite sustained hydrogen fusion, and the outward pressure from that fusion balances the inward crush of gravity, stabilizing the object into a genuine, long-burning star. A brown dwarf never quite gets there. Its total mass, typically somewhere between about 13 and 80 times the mass of Jupiter, simply isn't enough to compress its core to the temperature fusion requires. The gas heats up as it falls inward, then the contraction slows, and the whole object settles into a kind of reluctant equilibrium, glowing from the leftover heat of its own formation, but with no ongoing engine to keep that heat topped up. The existence of these objects was predicted decades before anyone actually found one. Back in the early 1960s, an astrophysicist named Shiv Kumar worked out that objects below a certain mass threshold should exist, forming the same way stars do, but never quite crossing into true fusion. For 3 decades afterward, astronomers searched and came up empty. Not because the theory was wrong, but because the instruments of the time simply weren't sensitive enough to pick these objects out from the crowded, noisy background of a normal sky survey. The breakthrough finally came in 1995, when a faint companion was detected orbiting a nearby red dwarf, and its spectrum showed something that settled the question immediately: clear signatures of methane in its atmosphere, a molecule that simply cannot survive in the much hotter atmosphere of a genuine star. Its estimated temperature came in at a little under 700 degrees Celsius, far too cool for fusion. After 30 years of searching, the prediction was finally confirmed. Failed stars were real, and if one had turned up orbiting a star just 19 light years away, the obvious next question was how many more might be scattered through the dark, completely unnoticed. That single confirmed discovery opened the door to an entirely new branch of stellar classification. Astronomers had to extend the traditional spectral sequence, the familiar run from hot blue O-type stars down through B, A, F, G, K, and finally the cool red M-type stars, with 3 entirely new categories to accommodate objects even cooler than the coolest red dwarf. L-type objects, with surface temperatures roughly between 1800 and 1000 degrees Celsius, shows something genuinely strange in their spectra. Signs of clouds made of condensed iron and silicate minerals, actual weather systems, but built from molten metal and vaporized rock rather than water vapor, drifting through thick, hydrogen-rich atmospheres. Rain on an L-type object wouldn't be water at all. It would be droplets of liquid iron, or grains of superheated sand, falling through skies far more exotic than anything found on any planet in our own solar system. Below the L dwarfs sit the T dwarfs, with temperatures roughly between 1000 degrees Celsius and minus 170 degrees Celsius, cool enough that methane becomes a dominant, defining feature of their spectrum, chemically linking these objects to the atmospheres of giant planets like Jupiter and Saturn far more than to any ordinary star. And below the T dwarfs sit the coldest confirmed category currently recognized, the Y dwarfs, with surface temperatures below roughly minus 170 degrees Celsius, and the very coldest known examples dropping below room temperature entirely. If you could somehow hold one in your hand, setting aside the small matter of its crushing mass, it would feel merely lukewarm rather than blazing hot. These objects radiate almost exclusively in the mid-infrared, wavelengths so far removed from anything visible that before space-based infrared telescopes existed, they were essentially undetectable by any instrument on or above the surface of the Earth, predicted by theory, required by the models, and functionally invisible to every observatory humanity had ever built. A survey worth knowing about here is the 2-micron all-sky survey, usually just called 2MASS, conducted between 1997 and 2001 using ground-based telescopes in Arizona and Chile, scanning the entire sky at near-infrared wavelengths and cataloging over 470 million individual objects. It became the definitive near-infrared reference catalog for the following 2 decades, and was instrumental in discovering the very first L dwarfs and T dwarfs, revealing objects that showed up clearly in infrared light while remaining essentially invisible at ordinary optical wavelengths. But 2MASS still operated at wavelengths too short to efficiently catch the coldest brown dwarfs. T dwarfs showed up faintly in its data. The coldest Y dwarfs, with their peak radiation shifted even further into the infrared, remained almost entirely beyond its reach, waiting for a mission built specifically to go deeper. That mission, as we covered earlier, was WISE, and it's worth adding one more layer to that story now that we've built up the full vocabulary of L, T, and Y dwarfs, because the scale of what it eventually revealed is genuinely staggering. NASA's current best estimate, built from years of follow-up analysis of WISE data combined with everything the Backyard World's volunteers have since confirmed, is that the Milky Way contains roughly 1 brown dwarf for every 3 to 4 ordinary stars. Given that the galaxy holds somewhere around 400 billion stars total, that ratio implies something on the order of 100 billion brown dwarfs scattered across the galaxy, drifting in every direction, an entire hidden population roughly comparable in scale to the number of stars in the galaxy, and the overwhelming majority of them have never been individually detected. And, given the sensitivity limits of even our best current instruments, may not be for a very long time. For every brown dwarf we've actually found and catalogued, there are almost certainly dozens more cooling quietly in the dark nearby, on trajectories that may be carrying them directly past star systems whose inhabitants, if any exist, have absolutely no way of knowing they're there. The James Webb Space Telescope, since becoming operational, has added a genuinely new layer to this story, not by surveying wide swathes of sky looking for new brown dwarfs, but by taking incredibly detailed spectroscopic readings of the ones we already know about. It has obtained detailed atmospheric spectra of WISE 0855, the freezing object we covered earlier, revealing signs of water vapor depletion and unusual ammonia chemistry in its frigid, alien atmosphere. The first direct chemical fingerprint ever obtained from an object this cold sitting, this close to our solar system. Webb wasn't built for wide-field survey work, though. It excels at deep, targeted study of individual objects, rather than scanning huge areas of sky, which means the job of finding the next generation of nearby brown dwarfs, the ones still too cold and too faint for anything currently operating to catch, will fall to whatever wide-field infrared mission eventually picks up where WISE left off. Let's talk a little more carefully about the biology behind all of this, because I mentioned Wien's law and eye sensitivity earlier, but there's more to the story of why human vision ended up shaped exactly the way it did. And it's worth understanding properly instead of treating it as some kind of throwaway detail. The human eye contains two broad categories of light-sensitive cells. Rods handle vision in dim light, but can't distinguish color, and cones handle color and fine detail, but need much brighter conditions to function well. Both types are sensitive only to a narrow slice of the electromagnetic spectrum, roughly between 380 nanometers at the violet end and 700 nanometers at the deep red end. That entire range, everything you have ever seen in your life, every sunset, every star, every face, every color on every screen, represents less than 1% of the full electromagnetic spectrum. Everything shorter than violet, the ultraviolet, the X-rays, the gamma rays, is completely invisible to you. Everything longer than deep red, the near infrared, the mid-infrared, the microwave and radio bands, is equally invisible. You are working with an extraordinarily thin slice of what actually exists, and even within that thin slice, your sensitivity isn't remotely uniform. Peak sensitivity under normal daylight conditions sits right around 555 nanometers in the yellow-green portion of that narrow visible range, and this wasn't some arbitrary starting point evolution happened to land on. It's a direct, traceable consequence of the star we happen to have evolved underneath. Our sun, at its particular surface temperature, floods the Earth with more photons in that yellow-green band than in any other part of the spectrum, and over hundreds of millions of years, the visual systems of every primate lineage leading eventually to us were gradually shaped, generation after generation, to catch those specific, abundant photons with maximum efficiency. This is adaptation working exactly the way it's supposed to. Your eyes weren't built to reveal the universe as it objectively exists. They were built to help a survival-focused organism track predators across open grassland, judge the ripeness of fruit hanging in a forest canopy, and read the subtle expressions on the faces of other members of its own species, all under the specific particular light this one star happens to produce. They succeeded brilliantly at that narrow task, and they were never under any obligation to also reveal the rest of the galaxy in the process. There's a broader point buried in this biological detail that reaches well past astronomy, and I think it's worth naming directly rather than leaving it implied. Every sense you have works this way. Your ears register only a narrow band of sound frequencies, missing entirely the ultrasonic calls bats and some insects use to navigate and communicate. missing the infrasonic rumbles elephants use to talk to each other across miles of open savanna. Your sense of smell, compared to a dog's, is almost laughably limited. None of this is a flaw, exactly. It's simply what a body built for surviving on one particular planet, under one particular star, actually needs, and nothing more. The universe was never designed with your perceptual limits in mind, and understanding that isn't a depressing realization, it's closer to a genuinely useful piece of humility. A reminder that the picture your senses hand you, however complete and convincing it feels in the moment, is always, necessarily, a curated slice of something much larger. Now, let's spend a little more time on Alpha Centauri, because we moved through it fairly quickly earlier, and this system deserves a closer look given that it represents our best real shot at a genuine sun-like twin sitting nearby. Alpha Centauri A and Alpha Centauri B orbit their shared center of mass roughly every 80 years, swinging between a closest approach of around 11 astronomical units and a widest separation of around 36 astronomical units. A range that puts their mutual distance somewhere between the orbit of Saturn and the outer edge of our own solar system at its widest. Alpha Centauri A is slightly larger and hotter than our own sun, while Alpha Centauri B is slightly smaller and cooler, an orange-tinted companion completing the pairing. Together, from far enough south on Earth to see them clearly, they appear to the naked eye as a single blazing point, and it takes a reasonably capable telescope to actually resolve them into the two separate stars they really are. The search for planets around this system has been going on for years, hampered mainly by the fact that the two stars orbit close enough to each other that their combined light makes it genuinely difficult to isolate the faint signal of anything small orbiting either one individually. The unconfirmed giant planet candidate detected in 2024 remains the most tantalizing lead so far, but confirming or ruling it out will likely take years of additional, painstaking observation, the same kind of patient, repeated measurement that revealed nearly every other object covered in this video. If a genuine, confirmed rocky planet is ever found orbiting either star in this pair, it would immediately become one of the single most significant discoveries in the entire history of exoplanet science. Not because it would necessarily be habitable, but because of sheer proximity. A real planet orbiting the nearest sun-like star system in the entire universe. Close enough that some of the more optimistic long-term propulsion concepts currently being studied could, in theory, eventually reach it within a human lifetime, unlike almost everything else on this list. That brings up a question worth putting to you directly, because I think it's the most interesting one this whole topic raises. If humanity ever does develop the kind of propulsion technology capable of reaching one of these nearby systems within a single lifetime, which one from tonight's list do you think deserves to be the actual destination? Not necessarily the most habitable candidate, but the one you personally find most worth the trip. Proxima Centauri, violent but genuinely the closest. Alpha Centauri, the closest thing we have to a true sibling of our own sun. Barnard's star, ancient and strange, racing toward us across the millennia. Or somewhere further out entirely, one of the brown dwarfs, cold and alien, and utterly unlike anything a human being has ever set foot near. Leave your pick in the comments, and if you've got a reason behind it, even better. Because I read through these, and I'm always curious which ones people actually choose and why. Let's look at what comes next. Because this story is nowhere near finished, and the next decade of instruments coming online are specifically designed to close many of the gaps we've spent this entire video walking through. NASA's Nancy Grace, Roman Space Telescope, expected to begin science operations in the coming years, will survey enormous swathes of sky with a field of view roughly 100 times larger than the Hubble Space Telescope, while maintaining similarly sharp image quality, and one of its major scientific goals is direct imaging and detection of planets around nearby stars, including many of the exact systems covered tonight. Ground-based efforts are advancing in parallel too, with next-generation extremely large telescopes currently under construction in Chile, mirrors spanning tens of meters across, designed in part to gather enough light from nearby red dwarf systems to actually characterize the atmospheres of small rocky planets orbiting them, searching for the same kinds of chemical signatures, water vapor, oxygen, methane, that would hint at genuine habitability rather than just a favorable position relative to a star's habitable zone. There's also serious ongoing discussion within the astronomical community about a dedicated successor to WISE, a new wide field infrared survey mission built specifically to push past its sensitivity limits and finally catch the coldest, faintest white dwarfs still hiding within our immediate neighborhood. The object's current instruments simply can't reach at anything beyond a few parsecs. Every serious estimate of our local stellar census includes an honest acknowledgement that more objects almost certainly remain undiscovered within 10 or 15 light years of our sun, not as a vague possibility, but as a near certainty based on the mathematics of how brown dwarf populations are distributed and how quickly they cool below the reach of current detectors. Whatever mission eventually catches those final holdouts will, in a very real sense, be completing a map that Friedrich Bessel started with a single patient star back in 1838. It's worth pausing on what it would actually mean if one of these ongoing searches ever turned up something conclusive, a genuine, confirmed biosignature in the atmosphere of a planet orbiting one of the stars we've discussed tonight. Given how heavily the nearby search has shifted toward red dwarf systems, purely because they're the easiest targets to study in detail, there's a real chance that if humanity ever does find solid evidence of life beyond our solar system in the coming decades, it will turn up orbiting one of these small, dim, red stars, one of the exact objects that spent the entire span of recorded human history completely invisible and unnamed. There's something almost poetic in that possibility, if it ever comes to pass. The first confirmed evidence that we are not alone in the universe might come not from one of the bright, mythologized stars every ancient culture built its stories around, but from one of the countless quiet, overlooked embers those same cultures never even knew existed. And it's worth being honest about the flip side of that possibility too, because responsible science requires it. It's entirely possible, maybe even likely, that the first few decades of this search turn up nothing but more dry, sterile, technically habitable zone worlds like the ones we found around Barnard's star. Planets sitting in the right place on paper while being scorched, airless, or otherwise hostile in practice. Confirming that a nearby world is not habitable is still a genuine scientific result, still worth funding, still worth reporting honesty rather than quietly, and it still narrows down exactly where the more promising targets are likely to be found. Negative results have already done exactly that work for us throughout this entire story. From the false planets around Barnard's star to the ghost world at Gliese 581, each disproven claim didn't set the search back. It sharpened it, forcing better instruments and better methods that eventually produced results that actually held up. So here's where we land after walking the entire length of this street tonight. We started with a single number, 60 or so suns within about 17 light years, 9 of them visible to your own eyes, and by now that gap between 60 and 9 should feel like something closer to a fact you carry with you than a statistic you briefly heard. Our nearest neighbor in the entire universe outside our own sun is invisible and dangerously volatile. Our second nearest spent a century producing phantom planets before finally yielding 4 real, uninhabitable ones. Our third and fourth nearest were entirely unknown to science until the last decade and a half, discovered not through any telescope pointed by a human eye, but through infrared surveys and, in no small part, through thousands of ordinary volunteers scrolling through images from home. And scattered throughout that same small neighborhood sit the quiet corpses of stars that finished burning millions of years ago, orbiting in plain sight beside the very brightest, most trusted star in our entire sky. None of this was ever a secret kept from you on purpose. It was simply a picture your own biology was never built to show you, tuned instead for one particular star, one particular planet, one particular slice of the electromagnetic spectrum, and nothing more. The instruments that finally corrected that picture, patient parallax measurements, cooled infrared detectors, citizen scientists working from kitchen tables, have spent the better part of 2 centuries slowly proving something that was true the entire time. The sky was never empty, and it was never finished being mapped. And if the last decade and a half has taught us anything at all, it's that the next name to be added to this list, the next hidden neighbor pulled out of the dark and finally given a designation, might already be sitting in a dataset somewhere right now, waiting for the right person, professional or otherwise, to notice it drifting where nothing was supposed to be. Tell me honestly before you go, which single fact from tonight actually changed how you think about the sky you grew up under? The invisible flares on our literal closest neighbor, the dead star quietly orbiting the brightest point in our sky, or the fact that our third closest neighbor wasn't even found until 2013. Whichever one it is, say why in the comments, because that's genuinely the part of making these videos I find most worth doing, and I'll be reading through every one of them.